Our planet floats in a cosmic neighborhood. It is a space filled with debris left over from the formation of our solar system. Most of these remnants are small, burning up harmlessly as shooting stars. But some are much larger. Throughout Earth's history, larger bodies have collided with our world. We see the evidence etched into the land as vast craters, silent monuments to ancient, violent events. Many of these impacts, however, struck the oceans. The vast blue expanse hides their scars beneath the waves. Their signatures lie in sediments, thin layers rich in shocked quartz, tektites, and iridium. Scientists drill the seabed, pulling up cores that record cataclysms. The Pacific, Earth's largest ocean, statistically bears the greatest chance of the next strike. Imagine a meteor, several hundred meters across, hurtling at tens of thousands of miles per hour. As it pierces the atmosphere, a searing fireball forms, compressing air into superheated plasma. In seconds, it crosses the sky and meets the sea. The moment of contact is not a splash. It is a colossal explosion of physics. The kinetic energy released dwarfs the total yield of all nuclear weapons combined. A shockwave tears through water at supersonic speeds. A massive, temporary cavity, miles wide, opens in the ocean. In shallower regions, it can excavate down to the seafloor. Water and rock vaporize, forming an enormous bubble of superheated steam and incandescent vapor. The bubble erupts upward, jetting a towering plume of steam, water, and debris. It climbs for miles, spreading a dark cloud across the upper atmosphere. Heavier debris and wet ash fall back as dirty rain. Some eject a return still hot. Near the site, steam and particulates shroud the sky. A deafening blast wave races across air and sea. Crater walls collapse inward. A central rebound jet surges upward. It crashes back down, setting the ocean into violent motion, and sets the stage for a mega tsunami. The meteor's violent displacement of water directly generates a tsunami. Unlike earthquakes that lift the seafloor, an impact behaves like a colossal stone dropped into a boundless pond. Initial splash and crater collapse launch powerful concentric rings. In deep water, tsunami wavelengths can span hundreds of miles. Wave heights remain deceptively small. Ships may scarcely notice. But the entire water column moves, storing vast energy. That energy carries the wave across basins at jetliner speeds. Seamounts and trenches refract and channel wave energy, focusing some shorelines while shielding others. A single impact can threaten coasts thousands of miles away. Hours of travel time create a narrow, vital warning window. Near shore, the front slows while the back surges. Water piles up. Wavelength shortens, wave height climbs exponentially. A low swell offshore can rise into a towering wall at the coast. At landfall, the tsunami arrives as a rapid, relentless rise of the sea. A sudden recession, an eerie warning, may expose the seabed. Then a surging flood races inland with devastating force. Buildings and bridges yield to the deep ocean's momentum. Ports are pulverized. Ships can be carried inland like toys. Debris-laden water becomes an abrasive, grinding torrent. Receding flows scour new channels and drag wreckage back to sea. Power, water, and communications fail. Isolation compounds risk. Roads and railways vanish, slowing rescue and recovery. Landscapes transform, beaches erode, soils salt, habitats smother. In densely populated lowlands with little high ground, losses would be catastrophic. Near the impact, shock, pressure, and heat obliterate life. A sterile dead zone spreads outward from ground zero. Tsunami-driven mixing shatters temperature and nutrient gradients. Coral reefs fracture and suffocate under sediment. Coastal nurseries, mangroves, and marshes are stripped away. Ejecta clouds dim sunlight, throttling photosynthesis. Plankton crashes ripple upward. Fish, mammals, and seabirds starve. Choked waters linger. Chemistry shifts may introduce toxins. Regional fisheries collapse, imperiling livelihoods and food security. Recovery could take centuries, or longer. Science gives us foresight, the power to predict and understand. Models simulate impact energy, crater formation, and initial wave fields. Then bathymetry steers waves across the basin. Outputs give arrival times, critical for warnings. High-resolution terrain enables inundation maps, extent and depth. Uncertainties remain, seafloor gaps, impactor properties, surf zone chaos. Validation against real events tightens confidence. Experiments refine physics. Models improve year by year. Each advance turns the unthinkable into a manageable crisis. Planetary defense begins with detection, cataloging near-Earth objects. Most pose no threat. When one does, time becomes our greatest asset. With years of notice, a small nudge can make it miss Earth, already demonstrated in space. If impact is unavoidable, the tsunami network, deep ocean buoys, and real-time data drives alerts. Effective systems translate warnings into rapid evacuation. Resilient design and vertical shelters save lives where high ground is scarce. Combined, deflection, detection, planning, these measures dramatically reduce losses. A Pacific impact is unlikely, but consequences are vast. Science transforms fear into informed action. Catalogs, models, and plans now exist. International collaboration builds a planetary immune system. Preparedness starts with each of us. Know routes. Have a plan. Stay informed. So, what would you do?